Okay, so this is a scholarship question from, I think, 2015, and it's called the vertical circle. So we have a small ball of mass m hanging from a light, inextensible string attached to a fixed horizontal post of radius r1 as shown. The first question says, show that the ball's speed at the top of its first swing must be at least that, so that the string remains taut. So this is a vertical loop, sort of, but because it's wrapping around this post, the string is going to be getting shorter, and so it's a vertical loop with a bit of a twist. And so we're going to then use the idea of that a minimum speed is required at the top in order for the string to remain taut, and that, remember, is the condition that mv squared over r is greater than or equal to mg at the top, but in this case r at the top is not the length of the string, it's the length of the string minus whatever's been wrapped around the post, because when it's at the top, if you look here, the string is going to have wrapped around and it's going to be like this. So the point that is pivoting around is this point, which is a quarter of the way around this cylindrical post. And so then we have mv squared over not r, but r minus a quarter of the circumference of this thing. So over r minus 2 pi, sorry, this is r2 minus 2 pi r1 over 4 is equal to mg for minimum. Right, so when it's the minimum speed, that's when we choose the condition that they're equal. And so that gives us then an equation that looks like this. We can cancel the m straight away. So we get v squared is equal to g times r2 minus pi r1 over 2, which is exactly what we wanted, right? So v is equal to the square root of g times r2 minus pi r1 over 2. Okay, cool. Next, we want to look at this one. So for the speed of the ball in A, show that the initial speed must be at least this. So in other words, the speed that it has here, just after it's been whacked, so it's been hit with a bat, so the ball wraps around. So the initial speed that it has to have there in order for it to reach this speed at the top. So this is an energy conservation problem, because we need the kinetic energy that it has at the bottom to be equal to the gain in gravitational potential energy plus the kinetic energy that it needs at the top to have this minimum speed. So we can say here that EK initial must be equal to GPE gained plus EK min top. Okay, so that means that 1/2 mvi squared has to be equal to mgh plus 1/2 mv min squared. All right, so what is the height that it gains if it wraps around like this? Well, the total height that we've gained is r2. It's not quite 2r2. This length here, that's r2 minus, what was it? pi r, oops, not equals, r2 minus pi r1 over 2. And then the last little bit that we've gained is this little bit here, which is just r2. Right, so the total height that it's gained is r2, oh, whoops, sorry, that's r1. r2 plus r1 plus this shortened version of r2. So let's write that in. H is equal to r2 plus r1 plus r2 minus pi r1 over 2. Okay, and let's just simplify that. That gives us 2r2 plus, or should we do minus? Yeah, let's do minus because that one's going to be bigger. So r2 minus r1 times pi over 2 plus 1. Right? Okay. So now we can plug in what we need here. First thing we can do again is get rid of all these m's just to make things a little bit simpler. And then we'll just multiply everything by 2. So we get vi squared is equal to 2gh plus v min squared. So vi squared is equal to 2g times 2r2 minus r1 times pi over 2 plus 1 plus, and v min squared is g times r2 minus pi r1 over 2. So let's simplify all of this, and hopefully, in fact, g appears everywhere, so let's try to get this into the shape we want. G, and then we have 4r2 minus, so 2 times r1 times pi over 2 is just pi r1, and then we have 2 times 1. I feel like I've got something slightly wrong in this thing here. Let's just look at this. 2r2, so that's this one and this one done, minus r1 pi over 2. That one should be plus, so this should be a minus. I think, yes, it should be. So this should be a minus. Okay, so this then becomes plus 2r1. That's that 2 times r1 times 1. Okay, and then we have plus r2 and minus pi r1 over 2. And this will hopefully simplify to that thing that we had in that bracket there. I might have done this slightly awkwardly, so pardon me if you see a simpler way. So g times, and then we have all the r2s, so we have 5 r2s. And then we have minus pi r1. And then how many r1s have we got here? So here we have r1, r1, and r1. So let's go with minus. So what have we got minus? We got pi plus pi over 2. So minus 3 pi over 2. And then we have minus 2 r1 is v, so vi is equal to that. Okay, so it got a bit messy just because of the minus signs, and I confused myself with those, but hopefully that makes sense. The thing is, the key just is to recognize that there are 3 separate heights here. That's the complicated part. Otherwise, it's just an energy conservation problem. And we've done this kind of energy conservation problem, for example, when we looked at the roller coaster loop. So at the top of the loop, we need to remember that it still needs to have some kinetic energy. Okay, so it says here, assuming an elastic collision, show that the speed of the bat is approximately half of the ball's initial speed. Okay, so we have a situation where we have a ball suspended from the string, and we have a bat that's approaching it with a speed v, and we'll call that b for bat, and we'll call this mass of the bat, and we'll call this little m. And then after they collide, we have the little ball is moving that way with a high speed. We'll call that little v, maybe, let's just call it little v. And we'll call this little m. And meanwhile, the bat has slowed down slightly. We'll call that big M bat. And then we'll call this V, big V bat final. Okay. So we're assuming an elastic collision. So we'll first assume momentum is conserved. So Pi equals Pf. And basically we're assuming no external forces. So no external forces. Which is an assumption because there is obviously someone holding the bat. But we'll just assume that in the little instant that the collision happens, the external force is small enough for it not to impact the conservation of momentum. Okay, also collision is elastic. That's stated. It won't be, but that's what we're told to assume there. So this is EK initial is equal to EK final. Okay, so we got those two conditions. So let's use the first condition. Condition 1 is Pi equals Pf. So in other words, M bat V bat, that's the initial, is equal to M bat V bat final plus M V. Now, because we're wanting to find out or kind of compare our ball's speed with the bat's speed, let's just rearrange this for the ball's speed so we get an expression for that. So if we rearrange this, we get mv is equal to mb vb minus mb vbf. So therefore v is going to be equal to mb over m times vb minus vbf. Okay, in fact that's called that expression 1. So there's our first expression for the velocity of the ball, which gives us a sense of how it compares to the bat's speed, but we still have all this mass included. Okay, then we'll use our second condition, which is that kinetic energy is conserved. So we can say 1/2, so this is momentum, this is EK, 1/2 mBvb squared is equal to 1/2 mBvbf squared plus 1/2 mv squared. And let's rearrange that for v as well, or maybe at least for v squared, so that we don't end up with a whole lot of ugly square roots in here. So if we do that, well, we can get rid of the half straight away because it's in every term. So we end up with mv squared is equal to mb vb squared minus vbf squared. And in fact, I'm just going to do this in one line, so I'm going to get rid of that m. Oops, let's keep the v and just divide by m here. Okay, we can call that 2. Now, one thing that we should be able to recognize here is that this thing here is the difference in 2 squares, which can be factorized out so that we have this expression in it. So then we would end up with mb over m times vb minus vbf as a part of this expression. So let's do that. So this is equal to mb over m vb minus vbf, so these are capital V's, times a vb plus vbf. Okay, but from 1 we know that this is equal to v, and so then we have v squared is equal to v times vb plus vbf. Then we can cancel this and this, so we get our final expression that the velocity of the ball is equal to the velocity of the bat, or the speed of the bat finally, plus the speed of the bat initially. And if we assume that the bat does not significantly slow down, we get v is equal to 2 v bat. In other words, or v bat is equal to 1/2 v, which is what we were trying to show. Okay, so that's a bit of a fiddly algebra question, but it does require us to use these 2 conditions and then to use a substitution, a clever substitution, to solve simultaneously and eliminate a variable. Okay, finally, as the ball completes the first orbit around the post, explain why the ball appears to be traveling at a speed greater than its initial value. So we can say, as it swings around, its radius decreases, due to wrapping around post. This causes rotational inertia to decrease, leading to an increase in angular velocity making it appear to travel at greater speed. Okay, so that's the scholarship question that I emailed you. Let me know if you have any questions about any step in that. But I think it's good if we carry on practicing some of these scholarship questions as we continue through the curriculum.